We just got through a video that was very difficult where I showed you how to start with the TDS equations and derive expressions for entropy change, S2 minus S1, for any ideal gas. Very complex. You had to make a decision. Do I have constant specific heat, variable specific heat? And so you've got that, and hopefully you'll have some homework problem experience with that. Now I'd like to talk about isentropic processes. Well, what's an isentropic process? That's one in which delta S is zero, isentropic, constant entropy. Delta S is zero. You think, oh, great. I don't have to mess with any of that stuff that we had from that last video. Let me give you a heads up and show you where we're going with this. So this module is about isentropic processes. And you'll notice here on the title slide, I've labeled it easy and hard. So the first part of this is going to be easy to understand. It's just a reminder to you about what is an isentropic process anyway? What kind of features make a specific process isentropic other than just being said delta S is zero? Okay, that's easy. And then I'm going to work you through isentropic processes for ideal gases. And there are some complexities associated with that in terms of determining the new state. If you're given the initial state and you're told the final state is or the process is isentropic, but determine the final state. And I'm going to try to show you some tricks of the trade on how to do that. But first, let's just talk about what is isentropic in the first place. Well, what's an isentropic process? It's a reversible adiabatic process. Isentropic process, reversible and adiabatic. Well, what does adiabatic mean? It means there's no heat transfer into or out of the system, into or out of the surroundings. In other words, fully insulated could be a synonym for adiabatic, no heat transfer. Well, what's a reversible process? A reversible process is one that can be reversed and leave no trace of having it happened both in the within the system or around the surroundings. That's a reversible process. So what does an isentropic process look like on a TS diagram? You got to have this nailed. Isentropic TS diagram. If entropy is constant, isentropic, then our process line is going to be a vertical line. So it's either going to be a vertical line going up or a vertical line coming down, one or the other of those. Either of those are isentropic processes. And so, of course, if you use your some common sense, I've shown you that lines of constant pressure, isobars, are swooping upwards, and the higher you go in pressure, the curves are higher as you go up higher in temperature. Okay, and so this process 1 to 2i here would be called an isentropic compression process because you're going upwards from a lower pressure to a higher pressure. Okay? So over here, here's another example of an isentropic process, but we're going from a high pressure to a low pressure, and that would be called an isentropic expansion process. Not big. It's kind of common sense if you think about it. All right, so you need to get good at visualizing in your head what does an isentropic process look like on a TS diagram. It's a vertical line. That can save your bacon coming up. Okay, let's look at an isentropic process for a closed system. What does that mean? What would your sketch look like? Well, the cylinder wall is fully insulated. And so in my sketch, it says no heat transfer between the closed system and the surroundings. So I have labeled Qn equals 0. So that, although I'm showing an arrow, I'm showing that it is adiabatic. Okay. The other part is going from state 1 to state 2. The process is, in the old days, quasi-equilibrium, chapters 1 and 2. And now you realize it's called reversible. And that means no friction between the piston and cylinder wall, and also no unrestrained expansion during the process 1 to 2. So that's a little review of what would an isentropic process be for a closed system. Now let's look at open systems that you've got some familiarity with because you've done some chapter 4 homework problems with this. Well, so here's my screenshots of various open systems that we've talked about. Okay, a compressor, a steam turbine, a pump, an air turbine, a refrigerant compressor. The equipment surfaces are fully insulated. So in other words, you have to imagine in your mind that all these pieces of equipment are fully insulated. And that's a pretty good model. That's going to be a pretty good model even for the real world. No heat transfer between the open system surfaces and the surroundings. Okay. Also, no internal friction within the equipment. So the shaft and the bearings there's frictionless between the shaft and the bearings as some shaft is turning around, right? No unrestrained expansion during the process. So you have to imagine, for example, the steam turbine cutaway, the air turbine cutaway. You have to imagine that these turbine blades are designed so perfectly that there's no unrestrained expansion. And we can just almost achieve that in the real world, almost. So no unrestrained expansion. So reversible adiabatic open systems. Yeah. Let's consider that that's a possible situation. Okay, that's the easy part. Now for the tougher part of this video. And I want to show you how to utilize isentropic relationships for ideal gas substances. So these are key relationships for ideal gases undergoing isentropic processes, not for any substance, but substances that are considered ideal gases. So I've tried to depict, here's my yellow text boxes and cautions. All the rest of this has to do with ideal gases undergoing isentropic process. Okay, so what I'd like to, so this is going to be just sort of some given information, and I'm going to try to chase you back to your textbook to get some background on this, because I've written down the integrated versions of the TDS equations for ideal gases with constant specific heat. Okay, and so kind of refresh your memory. Yeah, that's right. I sort of remember this from a previous video. I remember this from my textbook. And another thing I'm going to remind you of is, wow, all the way back, I think, to chapter 3, where we defined a variable called little k. And we didn't do anything with it, really. Okay. But we defined K as C sub P divided by C sub V. It's called the specific heat ratio. And so, of course, if you've got an ideal gas and you have C sub P is constant, do you see that K is constant? Because if CP is constant for an ideal gas, then CV is also a constant. I've written here. Okay. So if CP and CV are both constants, then K must be a constant. And we refer to K as the specific heat ratio. You can see it's CP over CV, ratio of specific heats. This is all kind of getting you ready for something here. Your textbook derives this, and I've marked it as important, but I'm not going to go through the video derivation to go from the set of integrated TDS equations for ideal gas constant specific heat all the way to the result. So I am going to give you the result and try to recommend that you go to your book to review this derivation. But for right now, here's the result. The result is for an ideal gas that has constant specific heat, CP is a constant number, undergoing an isentropic process, I can tell you that it turns out your textbook derives that P times little v, specific volume, to the K, CP over CV, is a constant number. Okay. This is an incredibly powerful engineering tool that I've written down in my green text box. For right now, you'll have to trust me, but when you go through homework problems, you get a quiz problem, and you're instructed, I've got an ideal gas with constant specific heat. It's undergoing an isentropic process. This is going to save you. Okay, so just go with me on this. PV of the K is constant for an isentropic process for any ideal gas that has a constant specific heat. CP is some number, and CV is some other number. All right. what I'd like to do is derive a relationship for you. And I'm not, and the book gives you the result, but I'm not, I want you to see how to go through this derivation because it's pretty easy. We'll say PV of the K is constant. We got an isentropic process, ideal gas, constant specific heat. So I'm going to write down, if PV of the K is constant, we're going from state 1 to state 2. P1V1 to the K equals P2V2 to the K, right? Equals some constant number. Now recall that PV is equal to RT. Remember that ideal gas equation of state. So over here on the left-hand side, I'm going to change V1 to RT1 over P1. That's just ideal gas equation of state. And I'm going to change V2 on the right side to RT2 over P2. Ideal gas equation of state, all to the K, all right? Let me collect terms. I've got P1 to the 1 and P1 to the minus K. So do you see here what I'm doing? I've got P1 to the 1 minus K. So I'm using algebra to simplify this, okay? Where's my R going? Shoot, where's that R going? Well, I'm dividing both sides by R of the K. That's where it's going. And one thing I did miss on the left-hand side, T1 to the K. So I'm writing that down. So do you see how I've got P1 to the 1 minus K, T1 to the K? And this is where I wish there were folks in the call. So of course, when I'm teaching the class, I try to reach out to the class and say, did you get that part? And most everybody will say, I think I got it, but I got to do some thinking about it. So, okay. All right. So we've got that. Here we are. So we're down to this P1 to the 1 minus K, T1 to the K, right? What I'm trying to do is drive towards a formula that says T2 equals, because it is very common in this class and in engineering to be given the P1 and T1 and P2, very common to be given those, P1, T1, and P2, to be told that it's an ideal gas undergoing a isentropic process, and your job is to find T2. That is a common assignment. So I'm going to try to show you how to do this. All right. Where were we? P1, we're at this step. The next thing I'm going to do is collect terms. Okay. So over here on the left-hand side, I've got a P1 to the 1 minus K. And over here, I've got P2 to the 1 minus K. So what I want to do is 2 steps at a time. I want to divide both sides by P2 to the 1 minus K. Okay. And then I want to flip P2 and P1. So instead of 1 minus K, I'm going to get K minus 1. So left-hand side, P2 over P1 to the K minus 1. So everybody got that? Okay, so that's algebra. The right-hand side, I'm going to divide both sides by T1 to the K. So I've got T2 over T1 to the K. All right, you good? All right, I'm almost there. I want to solve for T2. So how do I do that? Well, I'm going to use algebra again. I'm going to take the kth root. Each side, I'm going to exponent to the 1 over K. All right. So the right-hand side, T2 over T1 to the K divided by K is T2 over T1 to the 1. So I'm going to move this over to the left side. And then, of course, I got my T1 over here. Okay. So I've got T2 over T1. Then I'll multiply by T1. And then my left-hand side that I'm going to move to the right is P2 over P1 to the K minus 1 divided by K. Now, this is, I got to tell you, say, oh, my head's spinning. What the heck did this guy just do? That's the derivation. And so you might pause and sort of study the derivation. I'm pretty sure I'm right. I'm pretty sure I got it, because if I compare my work to equation 643, you'll see that they are identical. Okay, so if you look with your eyes, so this is identical to equation 643. But be very careful. If you write this formula down on your formula sheet, even the book, look at what they do. Look at what they do over here. They don't just write the formula down. They've got S1 equals S2. Isentropic, S1 equals S2, and constant K, ideal gas, CP over CV. So they didn't write out ideal gas because in their textbook writing, it was clearly in an ideal gas section. But very important, the way I've done it, if you're writing this down on a formula sheet, you write down your formula, hate to use that word, right? You got to write down these 3 bullet items with it. Isentropic process, ideal gas, constant specific heat, which means constant K. Got it? I hope. If you don't get it, just pause the video and study on this derivation. You start with PV, the K is constant, and you can do your own algebra to derive this relationship using the ideal gas equation of state. Whew. Got another one to derive for you. Okay. What I'm looking for is there are times, particularly when you're in chapter 9 and you're modeling internal combustion engine operations, internal combustion engine piston and cylinder computations for things like a diesel cycle or a spark ignition model cycle. Typically, in those situations, you're given T1 and little v1, and you're given V2, little v2, and you're told it's an isentropic process, ideal gas, constant specific heat. And your job is to find T2 for that isentropic process. It's going to be a little easier, but let's go through this derivation. Let's start PV, the K is constant. So P1 V1 to the K is P2 V2 to the K. What's P? P is RT divided by little v, ideal gas equation of state. So I'm going to put in, instead of P1, I'm going to put RT1 over V1, V1 to the K. Right-hand side in P2, I'm going to solve for, put it in terms of RT2 over V2, V2 to the K. Great. All right. Let's do some algebra and say, okay, well, here's a V to the minus 1. Here's a V to the K. So I've got T1, V1 to the K minus 1. I've divided both sides by R. Okay. And so then I've got T2, V2 to the K minus 1. All right, cool. I'm driving for T2. So I'm going to see, okay, I see I've got my T2. I'll move it over to the left, but it's going to be T1. And then I've got on my T1 side, I'm going to have V1 over V2 to the K minus 1, V1 over V2 to the K minus 1. But look, typically I like to solve for V2 over V1, sort of the 2 over 1 thing from 1 to 2, so 2 over 1. And so I'm simply going to flip the exponent, right, to flip my V1 over V2 into V2 over V1. So T2 is T1 times V2 over V1 to the 1 minus K power. Say, oh, okay, how did I do? Okay, sure enough, I've got exactly what equation 644 has. So just want to demonstrate to you that if you get stuck at the graduate level, if you're not allowed to have a formula sheet, you should not at the graduate level, you can start with PV of the K is constant, and you can derive 2 very powerful computational techniques to solve for T2 equals, as long as you've got an isentropic process, ideal gas, and constant specific heat. That's the big takeaway. Now I'm going to switch gears again. If I haven't confused you yet, I'll confuse you now. Now let's say we have an ideal gas with variable specific heat. So all bets are off with all that PV of the K equals constant stuff. If CP is variable, K is variable. So we can't use any of that stuff that I just talked about. So we go to section 611.2 in your book, and it says using the ideal gas model, but for air, for the substance air. It's an ideal gas, but with variable specific heat. It turns out, so I'm going to give you the old, it turns out in your textbook that for the isentropic process, you can show that P2 is equal to E, that's EX, E to the S0 T2 divided by R. Okay. So that's kind of complex. And this S0 was something I introduced way back in a previous video, this S0 for air. Remember, you're going to go to table A22 for air. It turns out that this expression, this computation that someone has done on a calculator, this S0 divided by R e to that, okay? That's called P sub R. We're calling that P sub R reduced pressure. I'm sorry, I think I misspoke. The relative pressure. The relative pressure is P sub R. So you're going to be able to find that in the back of your book in table A22 for air. The other very cool result, very powerful result, is equation 641 says for an isentropic process, well, for air, isentropic process, air with variable specific heat, PR2 over PR1 equals P2 over P1. Extraordinarily powerful because typically in engineering problems, you're going to have both P2 and P1. So if you can look up PR1 at state 1, which is typically given, say typically T1 is given, if you have T1, you can look up a value for the number PR1, solve for PR2, and that's what will enable you to back calculate T2. So let me see if I can give you an example. Okay, this little equation 641 is extremely powerful. It's in tiny little print in your book, very powerful. So I've written it out in bigger font here. All right, and I've tried to bring this home. I've drawn in my sketch. Okay, so I've drawn a sketch of my isentropic process, 1 to 2i. Remember, of course, it can be flipped. It can be the arrow can be pointing down just as well, but that's just your example. Here's a vertical line, isentropic process. We've got air. So for air, isentropic process, variable specific heat, you've got P2 over P1 identically equals PR2 over PR1. And similarly, V2 over V1 is equal to VR2 over VR1. What I want to do is show you a screenshot of table A22 to get you a little more familiar with dealing with this PR business. That's going to be some of the first homework problems you have, where the pressure ratio is known, you're given that it's an isentropic process, you're given that it's air with variable specific heat. So here's a screenshot of table A22. And let me try to get you somewhat comfortable here. Notice here these columns. Notice how these, so over here you've got H, U, and S0, all tabulated against temperature. And then you've got two columns that are kind of separated off. And notice here that there's a little note above PR and VR. It says when delta S equals 0. That means isentropic process. All right. So notice here, so we've got double columns. Remember, table A22, temperature increases in the left column, and then it gets so big that it sort of switches over to the right-hand side of the page, and T continues to increase. So let's just look over here, for example, at this leftmost side of the screen. So notice here, when delta S is 0, that means you can only use these columns when you have an isentropic process. Please commit that to memory. So you can't just be writing P sub R down for anything. It's got to be an isentropic process. Okay. And so notice that P sub R is a number that corresponds to a temperature. So PR as well as VR are simply numbers. They are unitless, okay, but they are a function of that kind of formula that you saw in the textbook, but they're a function of temperature only. All right. So I've tried to hit that home that these two columns that are walled off with those lines, they're only to be used for isentropic processes only. Well, we've come to the end of what started off easy video, what's an isentropic process, and turned into pretty tough, more material. Okay, so let's recap. An isentropic process is one that's reversible and adiabatic. That's important. That's not something you put down on a formula sheet. Okay, these fundamentals apply to both open and closed systems. Okay, and we also derived useful relationships for ideal gases undergoing isentropic processes. we had one block of relationships that applied to isentropic, ideal gas, constant specific heat. And then we had another block of relationships that applied to air, ideal gas, variable specific heat undergoing an isentropic process. Okay, so what started out as easy, what's an isentropic process, turned out to be something pretty complex. And the reason it's complex is because it's enabling you as an engineer to determine what is state two, what is T2. That's the key. That's what this is all about. So given information about state one, and given that you have an isentropic pressure, oh, and we gave you P2, find T2. That's going to be a very repeating problem that'll be a little bit of a problem in a larger problem for much of the rest of this course. And that's why I wanted to devote this much time to those relationships.